So in this case, let us construct our X. Okay, X would just be our collection of a TV, for example, and ones 201. Right, so basically X would contain two columns. The first column is actually I get it inverted. So the first column should be all the ones, and the second column should be TV, right? So that's the I think I got it backwards. Should be the TV and the ones. So because I want to make sure the first column is multiplied by A, the second column is multiplied by B, right? Well, in this equation, I can switch the first row and the second row without affecting anything, because the right-hand side is 0 anyway. Okay. So this is my X, and the linear, and also my Y is just equal to sales, is the thing I want to predict. And what I need to do is X transpose times X backslash Y. That's why did I? Oh, backslash not Y, but X transpose times Y. So this is the variables A and B I should get. Right, so now let's actually plot this data and hold on. And how do I plot the linear model out of this? So I already have this. So yeah, let's actually plot the TV and also this guy times TV plus that guy, right? So that is the linear model I construct out of this. So here turns out to be the best linear model I can construct using by minimizing the objective function. All right, and I can actually do better than that by incorporating a lot more variables. So if I put if I have the TV and I have the radio and I have the newspaper together, I can have the same thing. I can use the same formula to evaluate the linear model using the 3 predictors. Okay, and when I plot them, I can plot these. Now,
should we plot each one of them along the model, or?
Yeah, so let's actually plot it to see what we get, right? So let's plot at squares, this times TV, plus this times radio, plus actually minus this times newspaper, and finally instead of plus 7 I have to plus 2.9, and this is, let me hold on and plot the original sales. So this is the kind of agreement between the original data, which are the red circles, and the prediction, which is the blue lines. So now it becomes the question of how do we quantify how well we are doing? So what's the best way to quantify which model is better?
Plot the error of Y1.
Yes, actually just to plot the error, right? So what if we do, so this is let's say this is model 2 is equal to that, and our model 1 is equal to our original univariate linear model, which is that. And we can always plot the sum of sales minus model 1 square. That's the objective function we minimized, right? If we only have one variable. And if we have all the three variables, we can see that the objective function we minimized is actually about 4 times smaller. All right, so the second model is apparently better. So that's how we quantify the performance of these statistical models. And one interesting thing is that, do you think this number is always the smaller the better? Can you think of a scenario where you can train a model that is actually smaller in the sum of the error but is actually worse? Yeah?
There's a point that's far away.
When there is a point that is far away, maybe that's actually, that is the case, but that may be actually there is a bigger problem if it's actually that case. Yes?
If you have like overfitting. So,
what does it mean by overfitting?
So let's say you have like a line that can it's something you suspect is supposed to be linear, but there's some scattering.
Mm-hmm.
You can find like a best linear regression model,
Mm-hmm.
but then you can also, like, if you have like a 50th order polynomial, you can make your error basically 0, so that like it curves so that it touches every point.
Okay.
But then like it's too close because you have like it's no longer anywhere close to a linear.
Right. So I think that's a very good point. So let me actually try to demonstrate what can happen in that case. So that is I think what is said over here is that if I construct an X, that is simply a function of TV, but instead of having just a linear relationship to TV, I can put TV and the TV square and TV cube, etc. Right? For example, if I just have this three-dimensional, order 3 polynomial, I can already fit a model out of this. Right? So how do we do that? I can just do the same thing, right? And I can obtain a model. We can have a linear, quadratic, cubic coefficient, etc. And my prediction is actually easy to evaluate. It's actually X times A is my prediction, right? So that's the y hat I constructed over here. So this is X times A. That's the prediction. Now my model 3 is this prediction over here. Now I can plot my TV and let's say model 3 as dots. What I get seems to be now it's pretty clear it's a cubic function, right? And if we hold on and plot TV and sales, see, we actually get a slightly better prediction, right? So basically, the more nonlinearity we add to the model, the more degree of freedoms there are, and we can find a better and better fit to the underlying data. And you can see this by looking at the model error. So if we do this with model 3, it's actually, compared to our original model 1, it's actually better, right? But this actually, there is, at some point, this is going to end. And the reason is not because, the reason is because of the data is going to be finite. So when we give the model too much power, it is going to, it's the same as any optimization problem, it is going to exploit the form of this objective function and give you an optimal that is in some sense not real.